Hello everyone. Today we are going to start our Plaxis course. Plaxis is a very powerful tool to solve complicated geotechnical problems. It is available in two versions, 2D and 3D. Plaxis can be used for both design and research purposes. Before going further, we first need to know what is Plaxis. Plaxis is a commercial software program that uses finite element method to solve a series of differential equations in order to find an approximate solution for complicated problems. To understand Plaxis performs its calculations on steps. Or before we start that, as a finite element method, Plaxis is based on three main principles: equilibrium principle, kinematic principle, and constitutive relations. To understand the Plaxis performs its calculations in steps. Each step represents a percentage of the applied external load. For each step, the displacement corresponding to the applied load is calculated through the stiffness matrices. Then, the strength is obtained and converted into stresses through the constitutive relationships that describe the material behavior. If the internal stresses and the external loads are in equilibrium, the next step will start. However, if the equilibrium is not satisfied, your simulation will be terminated with an error. In general, any finite element software performs its calculations by dividing your problem or medium into a number of elements and start computing the stresses and strains at the nodes of these elements, and this is what we call meshing. It should be noted that the larger the number of elements or fine mesh, the more accurate solution that you can obtain. However, the computational time will be large. Therefore, we need to optimize our model in order to get an acceptable accuracy within a reasonable computational time. There are a huge number of elements available to form your mesh. In Plaxis, we use either these triangular elements for the 2D models or the tetrahedral elements for the 3D models. Before going deeper, it would be useful to discuss some of the basic concepts about the different constitutive models used to describe the material behaviors, and what is the advantages and disadvantages of each of them to help you find which of them is more suitable in your simulation. First, we are going to start with the linear elastic model. So for the linear elastic model, as we can see, as the stress increases, the strains also increase in a linear relationship. And if we remove the load, the strains go back to zero, which means no plastic strains. For the nonlinear elastic model, the stress-strain relationships is nonlinear. However, similar to the linear elastic, if you remove your loads, the strains will go back to zero and there is no plastic strains. For the elastoplastic model, the stress-strain relationship is also nonlinear. Plus, when you remove the load, the strains decrease, but it never go back to zero due to the presence of some plastic deformations, as we can see here. And the most famous one is the elastic perfect elastic model. In this model, the strain increases linearly with the stress until it reaches a certain threshold, after which the strains continue to increase at the same load. There is also the strain hardening constitutive model and the strain softening constitutive model, which we are going to discuss in detail in the course. The linear elastic model can be used or depends mainly on Hooke's law, and it can be used for stiff structure inside the soil like piles and footing. To use this model, we need to define two parameters, E, which is the Young's modulus or modulus of elasticity, and mu, which is the Poisson's ratio. As we can see from the figure in front of us, E can be calculated as the slope of the stress-strain relationship, or sigma over epsilon, where sigma is the stress and epsilon is the strain, is a vertical strain, epsilon 1, and the Poisson's ratio mu is the ratio between the lateral strain epsilon 3 and the vertical strain epsilon 1. Some alternative parameters that can be used instead of the modulus of elasticity and the Poisson's ratio is the shear modulus G, which can be calculated as E over 2 pi 1 plus mu, and the bulk modulus K, which can be calculated as E over 3 multiply 1 minus 2 mu, and the odometer Young's modulus, which can be calculated as E multiply 1 minus mu over 1 plus mu multiply 1 minus 2 mu. You don't need to worry about these alternative parameters in Plaxis, because like Plaxis automatically calculated once you give it the parameters or the values of the modulus of elasticity E and the Poisson's ratio mu. For example, if we choose our soil model as linear elastic as we see here, Plaxis will ask us to give him the values of E and mu. So if we assume E as 30 megapascal and mu as 0.3, we will find that Plaxis automatically calculate the values of the shear modulus G and the odometer according to the previous equations, as we can see here. After finishing the linear elastic model, we are going to talk about another model called Moore-Coulomb model. The Moore-Coulomb model is an elastic perfectly plastic model. But before we start speaking about this model, we need to clarify an additional parameters that we will need to use in our Plaxis simulation. These parameters called the dilation angle, or psi. To clarify this parameter, let's assume we have dense sand under a shear force. Because the particles of the dense sand are very close from each other, there is no place for these particles to move. Thus, we will notice that the sand particles will try to move on the top of each other, causing some increase in the soil volume, or what we call dilation, as we can see here. So, as an acceptable approximation for the value of the psi, we can assume the psi as equal to phi, which is the friction angle of the soil, minus 30. As we previously mentioned, linear elastic model can be used for a stiff structure inside the soil. However, to accurately simulate the soil behavior, this will not work, and some additional parameters need to be defined to account for the soil plasticity. For the Moore-Coulomb failure criterion we are discussing now, these parameters are the cohesion C, the friction angle phi, and the dilation angle psi. For example, if you define the Moore-Coulomb as your material model in Plaxis, you will find that both E and mu are the same. However, an additional section in the input window asks you to define the values of C, phi, and psi, so that the Plaxis can account for the soil plasticity. In conclusion, the Moore-Coulomb model is a linear elastic perfectly plastic model that depends on Hooke's law to define the soil elasticity, and on the more column failure criterion to define the soil elasticity. As we can see here, we can find that at the beginning of the loading, so the displacement or the strain increased linearly with the applied stress until it reached a certain point, after which the stress remains constant while the strains continue to increase. And this is the shape of the Moore column in the 3D space. So to model the soil in Blacksys using the Moore column model, you need to define these parameters. First, Young's modulus E, Poisson's ratio mu, the cohesion C, the friction angle, and the dilation angle. It should be noted that the chosen parameters for your model must be a good representative of the real soil condition to make sure that the soil behavior is approximated in the best possible way. So these soil parameters can be obtained either from laboratory tests like the triaxial test, undrained, consolidated drained and consolidated undrained, the odometer test, and the sample shear test, or from field tests like the SPT and the CPT. Can also be obtained from some empirical correlations, some tables and charts, and finally engineering judgment. It should be noted that the engineering judgment is very risky, so don't try to use it unless you have the required knowledge and experience to do so. In the previous slide, we mentioned that for linear stress-strain relationship, the modulus of elasticity is the slope of the straight line. However, for non-linear stress-strain relationship like the one we have here in the figure, every level of strain or point on that curve has its own elasticity or Young's modulus value. So, which value of elasticity I should use in our Blacksys model? This depends on your soil type and the level of strain you are expecting. So, for highly over-consolidated clay and rocks, or if the level of strains you are expecting is very small, you can use E0. However, for sand and normally consolidated clay, or when your level of strain is moderate, use the E50 shown here on the figure. If you don't have any stress-strain relationship for your soil samples and you want to get an approximate Young's modulus value for a preliminary design, you can get an approximate values using some empirical equations like the ones shown here. So for the E50, for sand soils, the E50 over P reference is equal to a range between 150 for loose sand to 500 for dense sand, multiplied by the square root of sigma 3 dash over P reference. If you have a medium dense sand, you can use some value in between. For clay soil, the E50 is equal to 15,000 multiplied the undrained shear strength over the plasticity index as a percentage. And the corresponding shear modulus G50 is equal to 5,000 multiplied the undrained shear strength over the plasticity index value. For the E odometer in sand, you can replace the sigma 3 dash in the previous equation by sigma 1 dash, and then you can get the E as a function of the E odometer using this equation. So E is equal to 1 plus mu, where mu is the Poisson's ratio, multiply 1 minus 2 mu over 1 minus mu multiplied by the E odometer value. Similarly, for clay soil, the E odometer is equal to 500 over the plasticity index multiply sigma 1 dash, and then you can get the E as a function of E odometer using this equation. You can also use some of the data and curves published in the literature to find an approximate stiffness value. However, you have to make sure that the conditions and assumptions used in developing this relation is applicable to your case. For example, Ermont et al. 1985 developed this curve that can be used to get the shear modulus of your clay soil as a function of plasticity index and underlying shear strength. Another curve developed by Duncan and Bushinami to determine the untrained Young's modulus as a function of the over-consolidation ratio, the plasticity index, and the underlying shear strength is presented herein. It is worth mentioning that these curves can only be used for preliminary design. As for example, if we have an over-consolidation ratio of 1.5 and the plasticity index less than 30, the EU over CU ratio varies between 600 and 1500. This level of uncertainty is not acceptable in geotechnical engineering. These are some tips you need to consider when you build your Praxis model. First, the cohesion value cannot be zero, even for cohesionless soil. This can be attributed to the presence of some element in the stiffness matrix that have cohesion or C in its denominator. So, if you divided any number by 0, this will give you undefined value, and this may cause some computational problems. So, if you have cohesionless soil with a real cohesion of 0, when you define this soil in Praxis, use a cohesion value of 0.2 kilopascal. For the friction angle, if you are looking for a quick model, like just to check your soil behavior, don't use a friction angle greater than 35, just to save like this computational time. However, when you are doing your actual design model, use the real value of your friction angle to like you obtained from your field or laboratory soil tests. For the dilation angle psi, use a value of 0 with cohesive soil. For dense sand with phi greater than 30, the psi is equal to phi minus 30. For cohesionless soil or loose sand with phi less than 30 degree, like psi cannot be less than 0. So if you have a phi less than 30, just use an psi of 0. At the end of this lecture, we are going to discuss the advantages and disadvantages of the Moore-Coulomb constitutive model. First, we will start with the advantages. Moore-Coulomb is a very simple and clear model. It is suitable for many practical applications. It has limited number and clear parameters that can be easily obtained from any laboratory or field soil testing. It is a good representative of the failure behavior, especially in case of drained condition. It can include dilation. At the same time, Moore-Coulomb model has some drawbacks that make it not suitable for all or some of the geotechnical applications. First, it assumes the soil as an isotropic and homogeneous material, which is not accurate for many applications. Second, the stiffness value is constant and is not stress or strain dependent. It uses the same stiffness value for primary loading, for the unloading, and for reloading, which is not true. The dilation continues with the same value until the end of your simulation. It has some problems in dealing with undrained soil response, and finally, it doesn't account for creep. In the next lecture, we are going to solve an example on Plaxis for a footing with a vertical and horizontal loads using the more column material model we discussed in this lecture. The soil properties we are using in our simulation are presented here. I advise all of you to solve this simple problem manually, and in the next lecture you can compare your results with what we are going to get from Praxis. Thank you.